Good.
Okay, our final speaker then is Denis Bartolo from ENS Lyon, and Denis will talk to us about active hydraulics. Denis, the floor is yours.
Thank you, Paddy. So before I start, I would like to do two things. The first thing is that I would like to thank all the organizers for giving me the chance to present our work today. And the second thing is that I would like to ask you a favor. I would like you to interrupt me during my talk. Please ask questions on the fly. I don't mind if I don't get to slide number 266. Okay, so please interrupt me. Ask questions or comment. There is no such thing as a stupid questions, but I can guarantee that I will give you some stupid answers. So it might be fun. Okay, good. So today I would like to tell you a little bit about active hydraulics. So to make sure that we're on the same page, I would just like to say a few words about conventional hydraulics. So I guess that we would all agree that hydraulics is one of the oldest branches of engineering. It was probably invented 8,000 years ago by the ancient civilizations of Mesopotamia and Egypt when they devised the first irrigation systems. And hydraulics is still very useful for the development of our modern societies. I'm just showing you here the map of the hydraulic network for the power water network in London as it was in the 60s. Okay, so hydraulics is a branch of engineering. I was myself trained as an engineer, but I'm now a physicist. And from a physicist perspective, I would say that hydraulics boils down to two fundamental laws. The first one is just mass conservation. And in steady state, whatever the complexity of your hydraulic network, you know that at every single node, the sum of all the currents has to be equal to 0. So mass conservation is definitely what the people from Mesopotamia and Egypt were using to design their irrigation channels. So that's rule one. The second rule was discovered much later in the mid-19th century by Poiseuille, Hagen, and Darcy. And the second law, for viscous fluids at least, is fairly simple. It tells you that the pressure drop across a pipe is proportional to the flux of fluid that can go through this pipe. Darcy's law. Okay? Good. So we have two laws. Both are linear, meaning that if I give you a pipe network geometry and a set of boundary conditions, you would just have to invert a big matrix and fully solve your hydraulic problem, meaning that you would be able to tell me what the fluxes are in all the edges of this network. Good. So we know how to do that. And we have known how to do that since the 19th century. So our lives could have been sweet and easy. But very unfortunately, for the past 15 years, a gang of troublemakers have decided to complexify our lives by making what we now call active fluids. So I'm not going to give you a formal definition of what an active fluid is. I would like to show you a couple of videos. So I will start with this video that I like very much, mostly because we have taken it in my lab. So what you can see here is just a collection of polystyrene beads. Their diameter is 5 micrometers. The beads are sedimented on a solid surface. And we now know how to turn these inanimate bodies into self-propelled particles. It's as simple as hitting a key on a keyboard. And what you can see on this real-time video is that as the particles interact, they self-assemble into a fluid. This fluid flows spontaneously. And after a short transient, you can see that the flow field forms this very stable macroscopic vortex structure. So we are talking about millions of particles interacting and self-assembling into this autonomous fluid. Okay, so this is not, of course, the sole example of an active fluid. That's not even the first realization. All of them can so I'm showing you again an example of a colloidal roller fluid. The cool thing is that because the pumps are embedded in the fluid itself at the level of its elementary units, it can flow even when it's enclosed in a loop. Obviously, you cannot apply a pressure gradient within the loop, and yet you can observe a flow. So earlier instances of active, earlier realizations were proposed here in Cambridge, in Ray Goldstein's group in particular. They decided to turn water into an active fluid. The solution is fairly simple. You just load your water sample with tons of bacteria, and provided that the channel in which you try to flow this fluid is shallow and narrow enough, you would observe a spontaneous laminar flow until the bacteria either die or would make too many babies. Okay, another solution was put forward by Zvonimir Dodzic. They also turn water into an active fluid by adding molecular motors and biofilaments in it. And even though you can see in this video, maybe you can see it, there are lots of fluctuations at short time scales, but on average, you can see that definitely have a net flux in the clockwise direction. Good. So I've shown you a couple of examples of active fluids. What I would like to stress on now is that the flows of active fluids are fundamentally nonlinear. It's a very simple statement. Flow rate, y-axis, pressure drop on the x-axis, and this thing can flow spontaneously with equal probability either in the right or left direction. Meaning that the flow rate can take the value +1 or -1, and we had a very hard time, okay, having these 2 points sitting on the same straight line going through the origin. Okay, so that's a nonlinear system. Good. So we wanted to be more quantitative, so together with Alexandre Morin, who is now a professor at the Lorentz Institute in Lyon, we measured the pressure flow rate relationship for this fluid. Yes? You can. Just be kind. Or try to. Like these little things, particles that just got stuck at the surface. Okay. So we also engineered like additional defects on purpose, and you actually need to add like a significant amount of defects to arrest this directed motion. I can tell you more about it later. Okay. So we measured the pressure flow rate relationship, and what you can see that over a range of pressure drops, the fluid just doesn't care. It flows at a given flow rate, and that's it. Okay, so we really have a bistable system. The current, okay, the mass flux is either plus J0 or minus J0 and basta. Good. So we understand how active fluids flow in pipes. Can we now try understanding how they flow in channel networks? So the first thing that we did was to make a channel network, starting from the simplest geometry that you can think about, just a regular square lattice. You have here 1,000 of connected microchannels. They are all the exact same geometry. And we filled this microfabricated structure with our favorite colloidal active fluid, and we just looked at the flow. So this is not a picture, that's a movie. Okay, it's now playing. And the fact that you can barely see anything moving tells you that very quickly the system reaches a very quiet steady state. Okay, it's super stable and it looks very homogeneous in space, and it is. When you measure the current distribution, so the current is measured within every channel, where you can see that the current distribution is very narrowly peaked on a single value. So what I told you before is true. The local current can take only 2 values. Okay? So we measured this quantity everywhere in space, and I can show you a current map. This is it. The thing is that this map is not unique. If you reboot your experiment, okay, you would find a different map. Okay, do experiment again, a different map. Repeat again, different map. So the steady states are strongly degenerating this system. And today, the question I would like to answer is, can we predict the morphologies of these active hydraulic patterns? Okay, that's my goal. Good. So to answer these questions, I need active hydraulic laws, like the combination of Darcy's laws and mass conservation for conventional hydraulics. So what are these laws? So first of all, I need a geometry. Okay, I've already told you that yeah, Eva? Remove this because, oh, sorry. I understand. Okay, thank you. Okay, yes, that's a lot of, sorry. Okay, thanks. So, geometry, square lattice. Yes.
Because you have some sort of hysteresis test. You have a range of pressures
That's right.
where you can't determine the direction.
That's
So
right.
if you drive it at a much higher pressure,
You will do everything.
which is somewhere within this range.
The system would pick up a flow direction. I would just flow steadily in this direction, however. Under which condition? Within the range of the hysteresis loop, I cannot tell you whether we did experiments here or there. I just don't remember, but I can tell you that if you work right at the threshold here, okay, you would see bending of the streamlines. Okay, you would see something like that. I can pull out some videos showing you how the morphology evolves as you increase pressure, applying a pressure against the mean flow. But basically, you can always define an average net flux. Okay? Good. So what was I saying? Yes, you need active hydraulic laws, okay, to predict the flow patterns. So geometry, okay. For the moment, let's focus on the square lattice. Two constraints. Mass conservation, okay, we are not working with radioactive particles, and you have this active flow constraint. The current is either +1 or -1. Good. So this tells you that we are dealing with a vertex problem. What is a vertex problem? Fairly simple. You can think about the flux as a spin, classical 1/2 spin living on the edges. Okay, it can take only two values. Okay, and you have this constraint here that tells you that you have a 2-in, 2-out rule. Okay, at every single node. Okay, you might want to call this an ice rule in analogy with spin ice physics. And the 6 possible current configurations that you can have are just shown here. You have 2 types of vertices, and I will use a lot the term green vertices, pink vertices. So I'm just going to take a second to show you the difference between the two. So 2-in, 2-out. In, out, out, right? The 2 inward fluxes, okay, are on orthogonal channels in the green configurations, okay? Orthogonal, 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 orthogonal. Pink vertices, okay, different configuration. Inward, inward, okay, align with each other. Good. So that's the 6 different possible configurations at every single node of your square lattice. Good. So the question now is it enough? Do I have enough information to predict the statistics of the flow fields that I've showed you before? Okay? Maybe, maybe not. To see this, we have to check whether all the vertices have equal probabilities. Okay? So we just looked at the flow. Okay? Okay, we mostly have green configurations. Okay, the probability of finding a pink configuration is much smaller than the probability of finding a pink one. Okay. So to establish our active hydraulic laws, we know that we have to deal with these 2 constraints. We now have to find out what is the statistical weight. Okay. And I would like to show you that there is no such thing as a first principle that can tell you what this probability distribution is, and that you have to do measurements, because this probability of finding a given configuration at a given node strongly depends on the local geometry of this node. So to convince you, let me show you 2 experiments. one in our bare square lattice. The second one was done in a channel network with the same colloids, same width, same everything, except that we have added these cylindrical posts, okay, at every intersections. Okay. Question: do we have the same flow patterns? Okay, so we run the experiment. You can measure the flow field and locate different possible configurations. And what you can see is that when you don't have any posts, you only have green configurations. When you add the post, you only have pink configurations. And that's fairly intuitive, right? If you add a post here, the particles would have a hard time following a straight line, okay? So you can think about these things as flow splitters. Good? Okay. So clearly, the geometry of the junctions determine the type of vertices that you can find. Okay, so we repeated the experiment systematically by varying the size of this path. So no path, mostly green. You increase the size of the path, more pink, more pink, more pink, and eventually you end up with a system where you only have the second type of vertices. You can be more quantitative and plot the probability of finding a given vertex as a function of the path radius, and that's what you find. Okay, so in principle we are done, right? We have these two constraints. We know what are the probabilities of finding a given vertex configuration, so we should be able to explain the geometry of the flow patterns. So first let me clarify what I mean by flow patterns. So let me show you first experiments performed in this channel where we have big splitters. You can measure the flow field everywhere, okay? It looks random, but it is not. If you take a closer look here, you would see that around each plaquette, you have a net circulation of fluid, right? And the circulation alternates. Okay. So basically, you have a local antiferromagnetic order. Okay, it's not, I'm not cheating here for once, okay? You can see that by plotting the circulation field at the scale of the whole sample, you have nice antiferromagnetic domains that are separated by domain walls, and I will tell you later what these domain walls are made of. Okay, so we have antiferromagnetic order. That's one type of pattern, circulation around the plaquettes. If you remove the splitters, look at the flow field, you can see here, for instance, on this plaquette, that you do not have any net circulation. Okay? And it's very clear, the macroscopic field, the system is fully disordered, you do not have any form of antiferromagnetic order. Good. So we have a standard order to disorder transition, antiferromagnetic when the paths and the splitters are big, disordered when you do not have any. Yes, Eva? Oh, they are not elongated. They are not elongated at all. It's optics. Look, this is the particle density. Okay, so the wake around the post is anisotropic, but the posts are not. Okay. Slow down, I think. Okay, the speed of a particle is around 1 millimeter per second, and the diameter is 5 micrometers. Okay, so they are very fast. They would run a marathon in a couple of minutes. Okay. Good. So, okay, ferromagnetic to antiferromagnetic transition. Good. So, can we explain the geometry now? In this case, okay, in the ordered phase, it's fairly simple. We only have pink vertices. Okay, that's just a fact. Okay. Square lattice, you don't have much of a choice. If you want to add pink vertices at every node, that's the only way you can actually tessellate your plane. So antiferromagnetic ordering, flow around the plaquettes, done. Yes?
This depends strongly on the fact that you chose a square lattice.
Absolutely.
If you were triangular or hexagonal lattice, you had a...
I'll show you over lattices later on. Now what I want to do is just to establish the rules that allows you to predict the flow, okay? No, but that's a fair question. I want to establish the rules, and I want to infer these rules from experiments. I'm just starting with a simple experiment, checking whether the rules that I've inferred are okay with this simple experiment first. Well, no problem. Good. So where we have a combination of the two possible vertices, square lattice, you end up with this type of pattern. What's the geometry? It's a mess, right? So it looks very complicated, and it is. Fortunately, we can call our StatMech friends at the rescue. And as it turns out, mathematical physicists and statistical mechanicians have been working to death on a model that is called the 6-vertex model. Okay? 6 vertices. They look very much like the vertices that I've already showed you, so I don't need to describe them. Because they do StatMech, they assign a weight to the 3 configurations. And the question is, okay, now how can I place all these vertices on the square lattice? Exactly the same question now as we are trying to answer. So our active hydraulic problem, okay, reduces to the 6-vertex model. Okay, so you do StatMech, you want to compute the partition function to see whether you have an actual phase transition in this system, to compute all possible structural correlation functions. The partition function is fairly simple. You just sum over all the configuration, weight of configuration A, the power n here is the number of vertices of type A, B, C, etc. In our case, B and A are equal, okay? Good. So it looks simple. Okay, this product, anybody in the room can compute this product. The problem is that it is very hard to sample the configuration space. Why is it hard? Because, okay, it's totally fine to place one vertex like this next to a vertex like that because they share the same arrow here on the edge, but you cannot have a vortex like this next to a vertex like that because they have a conflicting direction for this arrow, okay? So sampling the configurations is the difficult part of the job. Fortunately, Baxter, Killen, and Wu introduced a trick. And the trick is the following. You look at this vertex, you would see that it has a mirror symmetry. Okay, this is a mirror symmetry axis. Say, okay, let's cut the vertex. Let's cut it into 2 branches, 2 paths. Okay. I can do the same with the second vertex, 2 axes of symmetry. So I'm going to need 2 drawings, and I'm going to draw 2 paths. Good. 2 plus 2. Fine. Now, what they suggested was to simply to replace this drawing by this drawing, and this drawing by one of the 2. Okay. If you do that, what you see is that the allowed configurations are self-avoiding polymer loops that are closely packed. Okay, so we are just moving from a spin problem to a polymer problem. Okay, so we are back in Sam Edwards' backyard. And if you are a theoretical physicist, summing over loops, okay, is something that mathematical physicists love summing on loops. Okay, why? Because they can really go to town. They can use conformal field theories, analogy with stochastic linear evolution, Coulomb gas techniques, quantum gravity, you name it, okay? So why am I telling you this? Okay, I can barely read the names of these theories, okay? Why? It's simply because our particles are as smart as Baxter. If you look at the trajectories of the particles now, the Lagrangian trajectories, you would see that all the particles on the green vertex, all the particles in this channel take a left turn. The particles coming from this vertex take a right turn. What the Lagrangian trajectories do is the Baxter-Killen-Wu procedure. What they do on the other vertex class is exactly the same thing. The particles sitting next to this wall turn right. The particles sitting first next to this wall turn left. Okay, and you can again reconstruct the 2 classes of paths that were suggested by Baxter, Kidden, and Wu. Good. So what I'm trying to say is that the Lagrangian trajectories of the particles just form a closely packed soup of self-avoiding polymers. And the cool thing is that once you know that, you can compute whatever geometrical quantity you want, because this model is exactly solvable. So for instance, you can compute the gyration radius. So first of all, you can measure the gyration radius of the Lagrangian trajectories. You find an algebraic increase with the loop size. This is the theoretical prediction. This is an exact calculation, 3/4. So this result, I should say, is deceptively simple. Okay, you would expect 3/4 if you think about an isolated self-avoiding walk in 2D. If you are more familiar with this type of physics, you would rather think about something like a 4/7, which would correspond to the gyration radius of the hull of a percolation cluster. Why it is not this? If somebody knows about percolation clusters, university class, I can tell you why there is a connection here. The length distribution is also algebraic. Measurement theory agrees very nicely. You can try measuring quantities that are more subtle, like 2 points correlation function. The probability to find 2 points at a distance r on a given loop. The finite size effects are more prominent here, but there is a reasonable agreement with this theoretical prediction again. Okay. So let me summarize what I've just said. We wanted to establish active hydraulic laws. We started with a simple experiment on the square lattice. We measured the current distribution. What we found was that the current distribution was absolutely consistent with these two constraints: mass conservation, current equals ±1 on the edges. We measured the probability of finding the vertices, the pink and the green ones, based on the geometry of the channels. And with this, we found that the Lagrangian trajectories are self-avoiding polymers, and we have been able to compute their geometry. Okay. Question, how much time do I have?
3 minutes. Sorry, 8 minutes in total. Yeah.
3 minutes in total?
8 minutes to the end.
Okay, so I was super optimistic, mostly because I prepared my talk in the train. So I'm going to jump through all this. Okay. I'm going to, okay, it might be good to show you that. So let me tell you that these rules are not specific to the square lattice. Okay. I'm just showing you an example on the lattice with a higher coordination number. When you add splitters at the nodes, you find a nice antiferromagnetic order. You can define the circulation on every single plaquette. When you remove the splitters, you have a disordered structure. You can indeed map it on a loop, self-avoiding loop system. And thanks to our active hydraulic rules, you can actually compute the geometrical properties of these loops, and they perfectly match what we observe in our experiment. Okay, so it's what, 12, is it 12?
Cool.
Okay, 12, okay. Okay, so I guess that now the loops and self-avoiding polymers you might want to hear about as spaghettis. So I'm going to stop here and answer your questions if you have more. Before that, let me tell you that the experiments and theory have been done by Camille and Alexis. So Camille is a PhD student in my group. Alexis is a colleague who has mostly worked on numerical simulations. Amélie Chardac, who is now a postdoc at Brandeis, initiated the project and answered your question about what happens if you place these things on the triangular lattice. And with this, I thank you all for your attention.
Okay, so thanks, Denny, for a fantastic talk. David.
That's something that the scripture says I would want. So I thought the principal role of the hosts that define the channels was to pin topological defects in the flow field, and so now it's looking like the system can offer in addition to those generating sounds.
So the posts are really are useful. Have two roles. they have a practical role that they speed up the transition to the state, they shorten the transition time, okay? It helps the system finding its steady state. That's just super practical, okay? About the topological defect, adding, okay, that's not a pulse, that's a star, but whatever. If you add a shape here, okay, you of course modify the overall topological charge of any vector field that you would place in your channels. Okay, so indeed it changes the topological charge, and but as you have noticed it on this video, you can have topological defects like vertices, okay, away from the post, okay, and they do not act as attractors for the topological defects.
It seems that what happens is the self-organization of the within a channel into splitting.
Yes.
So, and so one question is, how does this lead to some fundamental rules about the flow? The other one, looking at this very picture, if I replace these very nice barriers that you put by circles,
Yes. Same.
you'll have frustration.
No.
Because you cannot now, if you look at it, then
no, I can tell you, no, we tried like circles, you can remove these things, it does not change anything, okay? So, so let me tell you just a little bit about this geometry. Where's that? All right. Okay. So let me elaborate really briefly on the triangular, on the case where the coordination number is odd. Okay. So if you have an odd coordination number, okay, exercise, okay, sum +1 and -1s, okay, and try to get 0, okay, with an odd number of +1 and -1s. You cannot do that. Good. So the system is indeed frustrated, okay, and this is really independent on the specifics of the geometry of the junction. The way the system accommodates frustration is by forming vortices, okay, in one branch. They flow. So the system, the fluid keeps on flowing, but there is no net flux across a branch that hosts a vortex or multiple vortices. Okay, that's one thing. In this triangular geometry, so the rule is actually not +1 -1, it's +1 -1 or 0. Okay, that's a general rule. Okay, so +1 -1, 0, and if you take a look at the corresponding vertex rule, okay, you find two types of vortices. Vertices, where you have two net fluxes, one vanishing flux, and a trivial situation where you have no flux at all. You can see that all these configurations, okay, must have the same statistical weight provided that the geometry, okay, of the node has at least this threefold symmetry. Okay, you cannot distinguish all. So the probability of all these vertices is just the same. Okay. Why this one has a smaller probability, and you can explain this, but I guess that was not I would not answer your question here. So the shape of the splitter, okay, is irrelevant provided that it has at least this threefold symmetry. Okay, and that's it. Okay.
I suppose here, if you replace your little cubicles by larger ones, yeah, so immediately you will not get any more by model distribution of the fluxes, but very soon you will get monomodal distribution, which will go down with the coarse graining which you have, yeah? With the fluxes, yeah.
Telling me. Okay. Yeah. Okay. Okay. Yeah. Yeah. So this depends. So for the antiferromagnetic configuration, that's something that you can compute by hand. Okay. In the disordered case, it's going to be algebraic because the phase is critical. Okay. So you have algebraic correlations everywhere, but I don't know how fast it would go. But it would definitely decay algebraically. It's going to peak at, if you average out something, it's going to be 0. Peaked at 0.
Patrick, I think your hand was up.
But post shorten the transients, and I wondered what if you could say something about transients, how it approaches this.
I believe that's a very interesting question. We have not investigated the transient in details. We have not studied the coarsening dynamics of the system at all. Okay. What I can show you in this video, though, is that you have both velocity and density fluctuations that are coupled in this system. I believe that the coarsening dynamics is going to be algebraic as well. There is no reason why we have this topological. Okay. Anyway, I believe it will have an algebraic coarsening dynamics, but I cannot prove it, and I can even show you experimental data.
Pietro, you had a question?
Yeah, so just a question. So in square lattice as a function of the obstacle, we showed the transition. So
yes.
What does the critical point look like?
Okay, so first of all, the disordered phase is critical itself. So you have a critical line. Okay? And the critical point, like in terms of morphology, what's the morphology of the critical point? So I believe that I've showed you a picture. Okay, it looks very much like this. So, oh, by the way, I didn't tell you what the domain walls are. It's related to your question. Okay, I didn't mention the domain walls during my talk because I didn't talk about the edges supporting no net flux. So deep in the ordered phase for this system, the domain walls are actually made of vertices with zeros. Okay. At the critical point, that's not what we see in our system. We have ferromagnet with fractal grain boundaries, and the grain boundaries are made of green vertices. As you get even closer, you have bicontinuous phase. Okay, but there is nothing really specific about the critical point. You can, of course, compute exactly what the critical point is. It matches what we see in our experiments, but this is not. As you have a critical line, this point has not unique properties.
Okay. I think one final question, then we should move to the next bit. Sorry, you could always ask it. Okay. One final question.
Changing the nature of the flow. Out object get an extensional point in the middle. But at any object in the middle, you remove the extensional point. So you're kind of changing your flow into a shear flow. So
exactly. That's why you have very nicely explained why it is more likely to find flow configurations, okay, with a stagnation point as soon as you add an obstacle. Okay.
Okay, and with that, can we thank Denis and all the speakers of this session?